Good evening. Today we are going into the third session of our third chapter, current electricity. And today's topics are, the first topic we'll be discussing is Kirchoff's rules, and then we go on to Wheatstones bridge, and the last topic for today will be meter bridge. Now, normally when you're given an electrical circuit with many resistors and cells, you can either see, we know the formulas for parallel connection of resistors and series connection of resistors. So you can use this knowledge or these formulas to solve for the equivalent resistance of a given circuit and thereby find the current in each branch of a given circuit. But there can be complicated circuits where this knowledge is not sufficient. So then we go on to what we have as Kirchoff's rules. There are two rules, Kirchoff's rules. The first rule is called the junction rule. Now, for the junction rule, in any given circuit, so we have our first topic for today as Kirchoff's rules. Kirchoff's rules. Now, the first rule called the junction rule deals with junctions or points in an electrical circuit. A junction in an electrical circuit is any point where more than two conductors are joined together. For example, suppose let's say we have a point A where we have a current I1 that is entering the junction. Then we have another conductor bringing in current I2 to the junction. Then let's say we have a third conductor I3 where the current is leaving the junction. Then we have a conductor carrying a current I4 which is leaving the junction, and a third one and a fifth one where the current I5 again is leaving the junction. So at this junction we have 5 conductors, 2 of them bringing in current. I1 and I2 are entering the junction. I3, I4 and I5 are leaving the junction. Now as you know, charges can never get accumulated at a point. So if charges can't get accumulated at a point, then obviously the addition of the two currents I1 and I2 entering must be equal to the sum of the currents leaving the junction. This is what you call as junction rule. For example, suppose this is 2 ampere and this is 5 ampere. We know that the total current entering the point A or that junction is 7 ampere. So then I3 plus I4 plus I5 must be equal to 7 ampere, because since 7 ampere current entered the junction, that 7 ampere current must leave the junction, because you can't have charges accumulating at a point or at a junction in the circuit. So we may write this as current I1 plus I2, the sum of the currents entering the junction must be equal to I3 plus I4 plus I5, because we have I3 and I4 and I5 leaving the junction, I1 and I2 entering the junction. So sum of the currents entering the junction must always be equal to sum of the currents leaving the junction, and this is what you call as the junction rule in Kirchoff's rules. Now we have the second rule, which is called the loop rule, and in the loop rule we are going to take closed loops in any circuit. If you have a closed loop in any circuit, it says that the potential drop across resistors and cells in a closed loop, the algebraic sum of this must be equal to 0. Now let me explain that with an example. We have here, I am showing you a circuit where we have a resistor here connected to a cell like this, and then here we have another resistor, and then we have a third resistor here connected to another battery. This is 12 volt, this is 5 ohm, this is 2 ohm, this is 3 ohm, and this is 6 volt. Now we'll call this as A, B, C, D, E and F. Okay. Now if you're asked to find out the current in each branch of the circuit, you may use this Kirchoff's rules, the first and the second. Now the second loop rule which I was talking about considers a single loop, closed loop like this. For example, B, C, F, A, B is a single closed loop here. Or you may look at this, C, D, E, F, C is a single closed loop here. Or the big one, B, D, E, A, B. This is also a closed loop. So we deal with closed loops in Kirchoff's second rule. And we say that the algebraic sum of the potential drop across resistors and cells must be equal to 0. So that means the potential drop across any resistor, the formula will be I into R is the potential drop V across any resistor. And the potential drop across a cell is directly given to you. 6 volt is given to you. So if you're talking about the potential drop here, we need to find the current here. So let's start here. We have a cell with a positive terminal of the battery. So I'm going to call that current as I1. We have another cell here with a positive terminal. And the current coming from this one, I'm going to call as I2. Now this current, when it reaches this point here, there are no other branches. So full I1 must go into this branch here, I1. Similarly, as I2 reaches point D, there are no other branches. So full I2 must leave here, I2. Now at this junction, we have current I1 and I2. Both are entering the junction. So the current that leaves from this junction must be the sum of the currents that entered the junction. I hope you understood. I1 entering here, I2 is also entering here. So together I1 plus I2 must leave the junction by the first rule. The sum of the currents entering must be equal to the sum of the currents leaving. Now at this junction, what will happen is current I1 plus I2 is entering. I1 goes into this branch and I2 goes into this branch. As I1 is in this branch here, I2 completes the circuit here. Okay. So we have current I1 plus I2 entering. The sum of the currents leaving is also I1 plus I2. Now to find the values of I1 and I2, the two variables, if you want to find out, you can go on to use the loop rule. In the loop rule, what it says is the potential drop across resistors and cells in a closed circuit should be equal to 0, the algebraic sum. So what we have here is this potential drop here will be, using the formula I into R, will be 3 I1. Then potential drop across a cell is 6 volt. Potential drop across the 2 ohm will be the current it carries is I1 plus I2. So 2 into I1 plus I2 will be the potential drop here. Then here it will be 5 into I2 because the current through this is 5 into I2 and the potential across the cell is 12 volt. Now because we said algebraic sum, we need to give signs to these potential differences. Now if you're going in this direction, we know that this end must be the positive and this must be the negative because current always flows from positive to negative. Okay, so I've marked this end of the resistor positive, this end of the resistor as negative. For a cell, you know this longer line will be the positive, the smaller line is the negative. Now here the current is in this direction, so naturally this must be positive and this end must be negative because your current is now going down. Here the current in this branch is going up like this. So here it must be the positive end and this must be the negative because you have marked your current like this. So this is positive and this is negative. For a cell here, this is the positive and the smaller line is the negative. So if I have marked the positive and negatives for all the resistors and the cells in the circuit. Now the rule that I am going to teach you is as you go in a loop, that is, let's take the first loop. Let's take B, C, F, A, B. That is, I am taking the closed loop B, C, F, A, B. Okay. Now as I go to the right, you can go in the clockwise direction or in the anti-clockwise direction. It doesn't matter. Here I am going in the clockwise direction. Here there is no resistor, so no potential drop. So I am not writing anything. Now when I enter here, I am entering through the positive. Here I am getting in through the positive. So I will write positive 2 into I1 plus I2. I1 plus I2. Then I reach here. There are no resistors here, so no potential drop. Now I reach the cell. Here I am entering through the negative. So I will write minus 6. And then I am entering through the positive of the resistor. So I am going to write plus 3I1 should be equal to 0. Where this 2I1 plus I2 is the potential difference across this resistor. The 6 is the potential difference across the cell that they've given you, and 3I2 is the potential 3I1. I'm sorry, the current that this carries is I1. So 3I1 will be the potential difference across this resistor. And I hope you understood that my rule, what I gave you as this rule is, as I go in, I'm entering through the positive of this resistor, so plus 2I1 plus I2, and here I'm entering through the negative, so minus 6. Here it's positive, so plus 3 into I1 must be equal to 0. So this is Kirchoff's second rule, which says the algebraic sum of the potential drop across resistors and cells in a closed circuit must always be equal to 0. Now let us look at this loop here, which is C, D, E, F, C. So we have this closed loop C, D, E, F, C. Okay. Now as I enter here, there is no resistor, so no potential drop. When I reach here, you will see I'm going to enter through the negative. So I'm going to write minus 5 into the current through that resistor is I2. So 5 into I2. When I enter the cell, I'm entering through the positive. So positive 12. Here there is no resistor, so I don't write anything. When I come here, I'm entering through the negative. So then we have minus 2 into I1 plus I2 must be equal to 0. 2 into I1 plus I2 must be equal to 0. Right? Yeah. So now I've got two equations. I've got one equation here and another equation here. And I've got two variables. I've got I1 as a variable and I2 as a variable. I can open the bracket, solve the two equations to get I1 and I2, and that's how you will use Kirchoff's rules. That is, the first one is called the loop rule, junction rule. Second one is called the loop rule, and you may use these two rules to solve and get the current in every branch of your circuit. So now what you can do is open the bracket here and then solve the two equations which you've done in class 10, solving for equations, and then you should be getting I1 here as 18 by 31 ampere and I2 you should be getting as 48 by 31 ampere. Okay, so you can try it out at home. I1 you will get as 18 by 31 ampere, I2 you will get 48 by 31 ampere, simply by opening the brackets and solving the two equations for the two variables. Now if you have difficulty, not a problem, we'll be solving such problems online. So at that time you can ask me your doubts. Okay, so we have this two rules, Kirchoff's rules. I hope you understood that as soon as you get your circuit, you please mark the positive and the negative end and then write your formulas. I will show you one more circuit so that you will be comfortable with this. Okay, now we have we have here 1 volt and then we have a 1 ohm here, then this is a 2 volt, this is a 2 ohm, this is 1 ohm, this is 1 volt, and this is 3 volt, and this is a 3 ohm. Okay, and then we have one resistance connected like this, which is a 3 ohm, right? Now let's call this as A, B, C and D. Now while you mark currents, you don't have to worry. You can mark your current direction as you like. It doesn't matter at all, except that you have to follow Kirchoff's junction rule. But in what direction do you take current, that's up to you. Now if you've taken the direction correctly, then what will happen is your answers will be positive. I1 and I2 and whatever you're finding out will be positive. Suppose you have taken the direction of current exactly opposite to what it is actually, then you will get a negative value. That's it. So it doesn't matter because, see now if you look at this, this is 1 volt and 2 volt. So here there is a 3 volt and a 1 volt. So it's difficult to find out in the beginning itself in which direction will be the current. If you have only one single cell, then it's easy because you just have to start from the positive of that cell and then go towards the negative of that cell. But in circuits where you have more than one battery or 2 or 3 batteries or cells, then what will happen is it's not easy to find out the direction of current. So what you do is start off with any direction, follow the junction rule, and then when you get your answers, if it is positive, it means that the current direction that you took was the right. If you get a negative answer, it means that the current in that branch was exactly opposite to what you've taken. That's all. Okay, now let me start here as this is, I feel this is a stronger battery. So I'm going to take current I1 in this direction. That's up to you. You may take it in the opposite direction, no problem. Now when you reach here, this current I1 goes in like this. So we have current I1 entering here. Now in this branch, actually this is the stronger battery and would prefer to put it like this. But I prefer, now let's say I took it like this. It doesn't matter. You can put it in this direction. Fine, no problem. Now I took it like this. So this I'm going to take as I2. So I2 coming in like this. That same I2 will flow in like this. And when it reaches this junction, current I1 is entering here and current I2 is entering here. I will take this as I1 plus I2. Now you can take this as I3, not a problem. But the thing is, if you have 3 variables, then you will need 3 equations and solve 3 equations. It will take more time and it will be tedious. So always try to keep the number of variables to minimum. So that is why instead of using I3 here, I took it as I1 is entering, I2 is entering this branch. So I1 plus I2 instead of I3. So I have only 2 variables and I need only 2 equations to solve for I1 and I2. So when I1 and I2, I1 plus I2 reaches here, I1 is going in this way and I2 comes into this branch. So I2 here, I1 here, together they flow as I1 plus I2 in this branch. Now to mark the current, the positive and the negative, we have this as negative and this as the positive. And since current is in this direction, so current is flowing from positive to negative. Here current is flowing in this direction, so this is positive and this is negative. Then this is a cell here, so positive here, negative here. The longer line is the positive one. Then this shorter line gives you the negative, this is positive. Now you see current in this branch is in this direction. So this has to be positive, this has to be negative because your current is flowing from positive to negative. The shorter line here is negative, positive. In this branch your current I2 is in this direction. So this must be positive and this must be negative. In this branch your current is in this direction. So this end is positive and I'll mark this end as negative. Right? Now since there are 2 variables, I need 2 equations. So I'm going to take 2 loops. Let's first take A, B, D, A, the first closed loop. So that's A, B, D, A that I'm going to write. When I start from here, I'm entering through the negative. So minus 2 into I1 because the current in this branch is I1 and the resistance is 2. Then I'm entering through the positive of the cell. Cell, already the potential difference is given to you. So plus 2. I don't have to multiply it with current. Then when I enter this branch, I'm entering through the negative. Can you see that? So this is minus 3 into I1 plus I2. So minus 3 into I1 plus I2. Then when I enter here, this is minus, I'm entering through the negative. So minus 1. And when I enter this resistor, I'm entering through the negative end of that resistor. This is the negative end because your current is coming in like this. So minus 1 into I1 will give me minus I1 equal to 0. So in this closed loop here, this is the equation you will write. Minus 2 into I1 plus 2. Then when I reach here, minus 3 into I1 plus I2 minus 1 minus 1 into I1 should be equal to 0. Now I need one more equation. So I'm going to take this loop here. So this will be B, C, D, B, C. Sorry, B, C, D, B. Okay. So you can start from any end you want. That's up to you. You can start from B or you can start from C. Doesn't matter. and you can go in the clockwise or in the anti-clockwise direction. So as I start from here, I'm entering through the positive. So this will be positive. The current here is I2. So 1 into I2 will be I2. Then I'm entering the negative of the cell here. So minus 1. Then I enter here through the positive. So that will be positive 3 into the current in this branch is I2. So that is 3 into I2. Then I'm entering through the positive of the cell. So plus 3. Then I'm going into this branch here. I'm entering through the positive. So that will be plus 3 into I1 plus I2 should give me a 0. The algebraic sum of the potential drops should be 0. So let's check once more. I started from here. Entering through the positive. So plus 1 into I2 is I2. Then minus 1. Then when I reached here, plus 3 into I2 because the current in this branch is I2. Then plus 3 volt. Then I go back like this. So this is plus 3 into I1 plus I2 must be equal to 0. So now I've got two equations. I can open the bracket, get equations 1 and 2, solve them to get the two variables I1 and I2. Okay. So that is Kirchoff's rules. And by the time we do the sums in the textbook, you will be fine with this topic. But I hope you have understood the rules that are used to get the equations in the two loops. Now our next topic is Wheatstones bridge. Again a very important topic because we have lots of application questions and problems based on that. Okay. Now your Wheatstones bridge is also important because it is the principle behind what you call as a meter bridge, and you will be doing meter bridge in the lab also to find out the value of an unknown resistance. So that's what we're going to do now. We have the Wheatstones bridge. Wheatstones bridge. Now this Wheatstones bridge is nothing but an arrangement of resistors along with a cell and a galvanometer, which will help you to find out the value of an unknown resistor. So we have resistance, 4 resistances like this. Okay. And let's call this as A, B, C, D. We have placed resistors P, Q, and let's call this as R and this as S. We have placed it along the arms of a quadrilateral. Between the two diagonally opposite ends, that is this B and D, we'll connect a galvanometer. And between these two diagonally opposite points, that is A and C, we'll connect a cell of volt V. Okay. Now, so this arrangement is what you call as a Wheatstones bridge. Now, if P, R and S are known values of resistance that is given to you, then you can find out the value of Q. For example, in the lab, you will be given a coiled wire and asked to find out its resistance. So to find out this unknown resistance, if P, R and S are known to you, you can calculate Q. This is what we are going to do. Now let's take current I coming from the positive terminal of the battery. When it reaches this junction, this current I has to split into 2. So let me take this as I1 and this as I2, so that I equal to I1 plus I2. When I reach this junction, this I1 again has to split. So I'm going to take the current IG, which passes through the galvanometer, and then I'm going to take this as I3. So that IG plus this I3 should be equal to this I1. Now here this IG and I2 are entering here, and let me say that is equal to I4. So IG plus this I2 is going in as I4, and here we have I3 and I4 entering together to give you the original current back to the battery negative. So this I hope you have understood that current I reaches here, splits into I1 and I2. I1 reaches here, splits into I3 and IG. IG and I2 together flow as I4 here. I3 plus I4 will enter as I and back into the negative terminal of the battery. Now if I am going to write Kirchoff's rules for A, B, D, A, that is this first loop here. Now I hope all of you know a galvanometer is a device that can detect if there is current or not. So this galvanometer will have a needle. So if your current is in this direction, let's say it will detect the current and let's say the needle moves to the left. If you reverse the current, then the needle will move to the right. And if there is no current, the needle will rest at 0. And that is what you call as null deflection of the galvanometer. So if there is no current through the galvanometer, then the galvanometer will show 0 deflection. And that is what you refer to as null deflection of the galvanometer. Now if I write, so there's Kirchoff's rule here. Here the current is I1 and the resistance is P. And since the current is in this direction, this will be plus and this is negative. So we have P into I1. Then when I enter the galvanometer, this is the direction of current. So plus and minus. So this will be plus Ig into G. Then when I enter here, current is in this direction. So this was the positive and this was the negative. So when I enter here, this should be minus I2 into R. So that is minus I2 into R must be equal to 0. So here, I hope you understood. Your current is in this direction. So plus and minus I1 into P plus Ig into G. But when I come here, I'm entering to the negative. So I put minus I2 into R. Because your current is in this direction, this is positive and this is negative. The same thing I'm going to do for loop B, C, D, B. That is this loop here, B, C, D, B. Your current in this direction would make this as positive and this as negative. Your current here is in this direction, so this is positive and this is negative. Okay. So I'll start from here. As I enter here, the current is I3, resistance is Q. So this will be I3 into Q. As I enter this, I'm entering to the negative. So minus I4 into S. So this is I4 into S. Then here again I'm entering through the negative. The galvanometer resistance is G. So that will be minus Ig into G equal to 0. Okay. Now I'm going to discuss with you what you mean by the balance condition. Balance condition of a Wheatstones bridge is when there is no current through your galvanometer. So if there is no current through your galvanometer, Ig is 0. And that condition of your galvanometer is what you call as balance condition of this Wheatstones bridge. Now, how you can bring about that is, you can adjust this P, R and S. You can adjust the values of P, R and S till your galvanometer shows 0 deflection. So, if you've adjusted the values of P, R and S in such a manner that your galvanometer shows 0 deflection, then you say that your bridge is in balance condition. So under balance condition, what will happen is, you will have Ig, that is the current through the galvanometer, to be equal to 0. Also, if this Ig is 0, then naturally I1 must be equal to I3, because current entering the junction is I1. What is leaving is Ig plus I3, and in that if Ig is 0, so naturally I1 should become equal to I3. Also, here current entering the junction was I2. So here Ig is also entering the junction and leaving is I4. So that means I2 plus Ig was equal to I4, and that Ig is 0. So we have I2 equal to I4. Right? Now I'm going to substitute all these conditions in my two equations here, and the equations that I'm going to get will be P into I1, and this is 0 because Ig is 0, and this I'm going to take to the right hand side, so I'll get I into I2 into R, which is my first equation. Okay, and then in the second one I have I3 into Q, so I have I3 into Q. This is taken to the right hand side and this Ig becomes 0. So that term is not there. Will be equal to I4 into S. That I take as the second equation. If I divide first equation with the second equation, here I will have I1 and this I1 and I3 we know now is equal because your Wheatstones bridge is in balance condition. So if I1 and I3 are same, they get cancelled, and I will get P by Q equal to, this I2 is equal to I4. I2 and I4 are equal. So then we have, this is equal to R by S, and this is what you call as the balance condition of a Wheatstones bridge. that is P by Q will be equal to R by S. So that's why I told you, if you now know P, R and S, values of the resistors P, R and S, then you can easily find out the value of Q. Because these three are known, you can get the unknown value of the resistance. So that is how you will use a Wheatstones bridge to find out the value of the unknown resistance. Now this Wheatstones bridge is for you to learn the theory, but when you get into the lab, the practical application of a Wheatstones bridge is what you have as meter bridge. And that's going to be our next topic, that is meter bridge. So let us look at that. Practical application of Wheatstones bridge will be the meter bridge. And you will have to do this in the lab this year when you get back to school. So we have meter bridge. Okay. Now in your meter bridge, we have, this is a thick copper strip which is used as the connection for resistors. Then here you have the resistor P. We have another thick copper strip here which will connect the P to your next resistance, that is Q. Then we again have connection wires which are thick copper strips. And then we have a 1 meter long wire. This wire is a high resistance wire which is 1 meter long, which is 100 centimeter. And from these 2 points, we have the cell that is connected. Now from here, that is, we will take this as point B, this as A, this as C, and we will now have a galvanometer which is connected to point D. Now this, if you see, is actually our Wheatstones bridge. Let me show you how. See, our Wheatstones bridge was like this. We have a resistance here, then here, and here. And in between these 2 points we have the galvanometer, and between these 2 points we have the cell. And we had marked this as A, B, C and D. This was our P, Q and R, S. Okay. Now if you compare this to this, you will see between A and B, that is point A and B, we have our resistor P, which is a known resistor. Then between B and C, see this, B and C, we have that unknown resistor, which I told you, your teacher is going to give you a thin coiled wire to find out the resistance of that wire. So that is that Q that we have connected between B and C. Then between B and D, we have the galvanometer. So between B and this D, we have the galvanometer. This is B and this is D. Then between A and C, we have the cell. So we have the cell between A and C, right? And these are all thick copper strips which will connect the resistors and the wires together. Now these copper strips are thick and using copper, so that the connection wires do not offer resistance, not much resistance, because as you know, R equal to rho L by A, copper has very low resistivity, and area of cross, because they are thick, then area of cross section is large. So low resistivity and large area of cross section would reduce the resistance offered by these connection strips, copper strips. But this wire here that we have, that is called the meter bridge wire, which I told you is 100 centimeter or 1 meter, is a high resistance wire. And I hope you have understood how we can compare this to this. So your unknown resistor, you have connected across B and C, okay, across B and C. Now let us look at this. Between A and D, we have the resistance R, and between B and C, we have the resistance S, right? Now because this is a high resistance wire, we know that R is equal to rho L by A, and this whole wire is made of the same material at the same temperature. So resistivity is a constant throughout the wire, and it's of uniform area of cross section. So A is also a constant, which means that the resistance offered by the wire is directly proportional to its length. Now here, this galvanometer is connected to what you call as a jockey. You will see that when you enter the lab, a jockey is just like a pen. It is all, um, it's the end here will be metal, but here and all it will be insulated. So you can hold it, nothing, no problem. Then one end of the galvanometer will be connected to point P. The other end of the galvanometer, there will be a screw at the end of the jockey. So this galvanometer will be connected to with a wire to this end of the jockey. The other end you can hold like a pen, and then you can slide from A till C on the wire. And because I told you this tip has this metallic contact, you will be that metal end will be in contact with this. Okay. Now as you slide your jockey to the right, you are going on increasing the length, and as the length increases, the resistance offered by that wire also increases. So here, if this is R, this length L is proportional to the resistance. As you go on pulling it to the right, this L is going on increasing, and the resistance R is also going on increasing. Now as you pull this to the right, you know that this length will decrease because it's 100 minus L. So this 100 minus L, that length of wire offers a resistance S. Okay. So between A and D in our Wheatstones that I drew here, we have the resistance R, and here we have that resistance represented by this much length of wire, of the meter bridge wire. And between D and C of our Wheatstones bridge, we have this resistance S, and that resistance here is offered by this length of wire, 100 minus L. Now we may write R is proportional to L, right? Because here we know this R is proportional to the length L. We also know that this S is proportional to 100 minus L, because this length of wire is proportional to the resistance S. If I divide the two, then I know R by S must be equal to L by 100 minus L. Now what you are doing in the lab is, you are holding the jockey and pulling it to the right and stopping at D. That is when your galvanometer will show null deflection. So you will keep on pulling till, or sliding the contact over the wire till your galvanometer shows null deflection. Why should you stop when your galvanometer shows null deflection? Because that is balance condition of your bridge. Your meter bridge is in balance condition when there is no current through the galvanometer, and that is called as a balance condition. So at some value of R and S, you will see that you have brought your meter bridge under balance condition. So when your galvanometer shows null deflection, you will stop, and that length you will measure as L, and the remaining length will be 100 minus L. So at balance condition, we already derived P by Q equal to R by S. In Wheatstone's bridge, I had already shown you under balance condition P by Q equal to R by S. Now if I compare these two equations, R by S is equal to L by 100, R by S is also equal to P by Q. So I may now write P by Q equal to L by 100 minus L, right? And from this equation, we know Q should be equal to P into 100 minus L divided by L, and that is how you will find your unknown resistance. So you would have been given an unknown resistance here and asked to find out its value. So all you have to do is make your connections correctly, take the jockey, pull from the left end to the right, and stop when your galvanometer shows null deflection, which means you've brought your meter bridge under balance condition. And then when you take this reading, that will be taken as the L value. Remaining 100 minus L will be this resistance here. And in your value, you can find out that Q, because P will be a resistance box, which is known value, and L you have measured. So P into 100 minus L by L will give you the value of that unknown resistance. Okay. So we have completed 3 topics today: Kirchoff's rules, Wheatstone's bridge, and meter bridge. All of them very important topics when it comes to application questions and problems. So please go through this video and we'll do the application questions and problems on that online. Thank you.